Okay, anybody have any homework questions you'd like me to go through? So there are three more things for vectors that I need to go through, and then we'll start going back, and it's going to look very familiar. We're going to define position, velocity, and acceleration, just like we did in 1D, but now all those things are going to be vectors. Okay, so first we need these three things. So this is how to do vector math using components. Yeah. Okay, so the first thing we have to be able to do, okay, try to remember this from lab. What do you think is the first mathematical calculation we have to be able to do? Adding two vectors. I think I heard someone say that, not really. So in lab, we talked about how to add two vectors. You have to think of each one as like part of a trip, and then the sum is the shortcut of the whole trip. But if you have the components of the vector, it's easy, and it means the same thing. The vector AB plus the vector CD is just equal to the x component of the sum is A plus C, and the y component of the sum is B plus D. And it's kind of cool that simple calculation means the same thing as that kind of complicated intuitive idea. But that's what they are the same thing. So for example, if you have a vector 5, -5, and you want to add it to the vector 1, 6, the sum is 5 plus 1 for the x component, -5 plus 6 for the y component, and so there you go. The second thing we have to be able to do is multiply a vector by a number. And so if we have a number C and we're multiplying it to a vector with components A, B, what we get out is, what we do is just multiply the C times each of those components. So we get, our answer has an x component of CA and a y component of CB. And in lab, we talked about the intuitive meaning of multiplying a vector by a number, and this does the exact same thing, just as a calculation. So now, for example, we can put these together. So what if we add, what if we want to know what 3 times -4, 1 minus 4 times 2, -2 is? Okay. Well, the order of operations rules say we do the multiplications first. And so we can rewrite this as 3 times that first vector, so -12, 3, plus, and we can multiply -4 times this vector to get the other thing. So -8 for the x component, +8 for the y component. Is everyone with me on that? And now you're just adding those two vectors. So we get negative 20 for the x component, positive 11 for the y component. And the last calculation that we're going to have to be able to do sometimes is to calculate the magnitude of a vector where you have the components. And so if we have a vector u that's equal to, that has components a, b, then the expression or the notation for the magnitude of a vector is the absolute value symbol. You can think of like the magnitude of a vector as like the absolute value of a vector. So the magnitude is equal to a squared plus b squared square root. Okay, so let's do an example of this. Let's say that we want to calculate the magnitude of the vector 3, negative 4. Well, that is 3 squared plus negative 4 squared, all square root. 3 squared is 9, 4 squared is 16, so this comes out to be the square root of 25, which is 5. Okay? And if we sketch this out, you can see why this works. It's just the Pythagorean theorem. If we have a coordinate system like this, and our vector is 1, 2, 3, 1, 2, 3, 4. Our vector is this. Okay. And what that 3 and negative 4 mean is this length is 3. This length goes in the negative direction and it has a magnitude of 4. And this makes a right triangle. And so it's the Pythagorean theorem. We're just calculating the magnitude of the vector is just the length of that hypotenuse. Okay, so if you remember that, it's easy to remember how to calculate the magnitude of a vector. Anybody have any questions about those calculations? You can see why it's helpful to calculate components of a vector instead of trying to do all these calculations by carefully like measuring lengths and angles and using the intuitive rules of adding and multiplying vectors. That would be a super huge pain. This is really quick and easy. Okay, so now that we have what we need to know about vectors, we're getting into 2D kinematics of particles. And to do that, we have to define position, velocity, and acceleration as vectors. Okay, in 1D we define them as numeric values, but now we're going to define what the position vector means. That's what that over arrow is. Velocity as a vector, and acceleration as a vector. So I'm going to start with the position vector. So does anyone remember when I introduced position in 1D kinematics, I drew a picture of a train, and I said that there are two things that you have to choose before you can define the position as a number. Anyone remember what that was? You have to choose a position equals 0 location, and you have to choose which direction is positive and then which one is negative. Okay, so, and you can think of those as stickers that you put down in the real world. We're going to choose the two-dimensional versions of those. So the two-dimensional versions of the 0 position and the positive direction are an origin location, you know, the origin of the coordinate system, and the orientation of the coordinate system. Can you see how choosing the origin is kind of like choosing the position equals 0, and choosing how the coordinate system is oriented is kind of like choosing what your positive and negative directions are, just expanded into 2 dimensions? So remember that this is analogous to choosing the position equals 0 and the positive direction in 1D. And this is, you have to make these choices in the real world. This isn't a mathematical thing. This is like stickers. Once you've chosen those, the position vector P is the vector from the origin. I'll call it the coordinate system origin. No, that's not what I wanted to underline. From the coordinate system origin to the object. Okay, so if this is our coordinate system and this is our object, then the position vector is this. And the easiest way to think of the position vector is this. So remember this. The components of the position vector are just the coordinates of the object. Okay, so it really is a vector, but you can just think of calculating those values as calculating the coordinates of where the object is at a location. So for example, if your coordinate system is this, and your object is here. The coordinates of that point are 4, 3, no, 4, -3. So the position vector is 4, -3, just written with that different notation for vector components. Anybody have any questions about that? Okay, the units for position, and we're going to see this with every quantity. Yes? Yeah, am I going too fast? Okay, so the units for position are units of length. And I was going to say, we're going to see this with everything in 2D. Whatever the units were in 1D, it's going to be the same units in 2D. I'll keep writing them, but you know, it's going to be length for this, length over time for velocity, etc. So the SI units for position are meters. And that's about everything we have to know about position. So just remember, you have to choose the coordinate system before you can do it. You have to choose where the origin of the coordinate system is going to be in the real world. Are you going to put it on the ground, underneath where the object starts, you know, that kind of thing. And you have to choose, is my x-axis going to be along the ground or up or down or whatever. But once you choose those, the position vector is just the coordinates of the object at a given time. Okay, so now velocity. So the velocity, just like it did in 1D, measures how quickly the position vector is changing. So it measures how quickly that position vector is changing. What that means is if you have a velocity vector of 0, 0, the position is just staying the same, okay? So if you have a velocity vector of 0, 0, then the object's just staying in the same spot. And that means that the position vector isn't changing. Now, I've said this before. I said it in lab and I said it on Tuesday in class. Remember that all vectors have two properties. Those are magnitude and direction. For the position vector and the acceleration vector, it's not super helpful to think about it that way. But for the velocity vector, it is. So it's helpful to think of the velocity vector this way, breaking it up into magnitude and direction. So for the velocity vector, the magnitude of the vector is the object's speed. And the direction of the vector is the direction the object is moving. And that was the case in 1D also. Remember the magnitude. So in 1D, if something had a velocity of -6 meters per second, the magnitude of that is 6, and that was the speed, 6 meters per second. And the direction says that the object was moving in the negative direction. Okay, so now we have a version of that in 2D also. The units for the velocity vector, just like in 1D, are units of length divided by time. And the SI units are meters per second. Okay, now there are 3 important facts that you need to keep in mind about velocity that's going to help us when we get to problems. So 3 important facts about the velocity vector. The first one is often in problems, the velocity isn't going to be given as components. We're going to be given a direction and a speed. So often we will be given the velocity vector as, I guess I'll write it as a speed and a direction. So for example, a problem will say, at the start of the motion, the object is traveling at 10 meters per second at an angle of 30 degrees above the horizontal. And we'll want to put that into components to do calculations. And so our job then will be to say, okay, well, we know that if we choose a coordinate system with the x-axis horizontal, which is going to be pretty common, then the object has a velocity vector like this, where this is 30 degrees and this is 10 meters per second. And so the velocity is 10 times the cosine of 30 degrees, 10 times the sine of 30 degrees, and that comes out to be 8.66, 5.0 meters per second. So most of the time in problems, your velocities you're going to have to get from a speed in a direction like that. Okay. And just to get you used to the way the notation that we're going to use, we're going to, so this is the velocity vector, but usually in the calculations, once we have everything in components, we're going to break calculations up into x calculations and y calculations. So we would then use this in equations as like v sub x, the x component here, is equal to 8.66 meters per second. And v sub y is equal to 5.0 meters per second. Okay, so that's the first thing that you need to remember about the velocity. The second thing is if an object is dropped, then at the instant it's released, its velocity, this sounds familiar, right? Its velocity is the velocity of what it's dropped from. Or let me just, to make it less wordy, its velocity is the same as what it's dropped from. So if an object is dropped from the window of a car that's moving 50 miles per hour horizontally, at the instant you let go of it, the object is also moving horizontally at 50 miles per hour, okay? And then that might change really fast. If you drop a balloon out of a car going 50 miles an hour, a tenth of a second later, it's going way slower than that. But right at the instant you let it go, it's going the same as the car. Okay, well, that's actually my example is something like that. So let's say, so if a ball is dropped from a vehicle that's moving 20 meters per second horizontally, then at the instant it's released, if we draw a coordinate system like this, the ball's velocity is horizontal. At 20 meters per second. Okay. Well, what are the components of that vector? Remember, I put the tail at the origin, so the components of that vector are just the coordinates of the head. So what's the x coordinate of the head? 20, yep, positive 20. And what's the y coordinates of the head? 0. And then once we figured that out, now in calculations, we would use the x component as 20 meters per second and the y component as 0. Okay, the last big thing to remember is in 2D. So this is also similar to something we've seen in 1D, but in 2D, when a projectile reaches its highest point, okay, remember in 1D, at the highest point, the object's velocity was 0. Now, you have to be careful with this. I know if you had to guess, you would probably guess the velocity vector is 0 at the object's highest point. It's not quite like that. What happens at the highest point is that the y component of the velocity is equal to 0. The x component of the velocity is not 0. Not necessarily. You can't assume that the x component of the velocity is 0. And if you want a sort of an intuitive understanding of why the x component isn't 0, think of like a pro baseball player in the outfield, like throwing a ball towards home plate. Okay, so this guy's just thrown this ball, right? And he's thrown it really fast. And say that you somehow knew where the ball was going to reach its highest point. Okay? And what you did is you put a ladder out there. And you stood up on the ladder. I don't know why you're so short. But this is you. Yeah. Okay. So you put a ladder out there. Yes, that is correct. And so you wanted to prove that when this ball reaches its highest point, the velocity is equal to 0. Does this look like a very good idea? You know, it's not a good idea because if this person throws this ball at 100 miles an hour, when that ball hits your head, it's not going to be moving up or down at all. The y component is going to be 0, but it's still going to be going 90 some miles an hour horizontally. Okay? If the x component of that velocity was 0, this ball would just gently nuzzle up against your head and be exactly stopped at the instant it got to your head. But intuitively, you just know that's not what would happen. Okay? And the reason for that is this. Being at the highest point doesn't have any effect on the x component. Okay. Don't do this. So I want this class to be about physics, but I also want to give life advice. Got it. Okay, so go through your notes. Remember these 3 things. These will help when we get to problems. And now the last thing we have to talk about is the acceleration vector. And acceleration, just like in 1D, is a measure of how quickly the velocity is changing. So acceleration measures how quickly velocity is changing. And this is something that was true in 1D and it's true in 2D. Constant velocity and zero acceleration mean the exact same thing. Okay, so if the velocity is not changing, then acceleration is zero. Okay, now here's the trippiest thing. I've saved the trippiest fact for last. There's a whole new thing that acceleration can mean that we haven't seen yet. So remember that in 1D, non-zero acceleration means the speed is changing, and that's the end of it. In 2D, non-zero acceleration means, so it can mean that the speed is changing. But it can mean also, so let me write it as and or. It can also mean that the object is turning. Okay, so in 1D, if an object is accelerating, the speed is changing. There's no denying that. In 2D, though, an object can be accelerating even if the speed is constant. And you kind of know that if you imagine like driving around in a circle in a big parking lot. You know the feeling of acceleration. You're being kind of thrown to the side as you turn around in the circle. Even if your speed stays exactly the same, what you're feeling is the acceleration that comes from the car not traveling in a straight line. It's turning. Okay? So this means that the direction of the velocity is changing. Okay, the units for acceleration like always are length over time squared. And that means that the SI units for acceleration are meters per second squared. And there's one, one thing to notice about acceleration. If an object is in free fall or projectile motion, the acceleration vector is always 9.81 meters per second squared down. So if you choose your y-axis to be up, which is what I'm usually going to do, then the acceleration vector is always 0, negative 9.81 meters per second squared. And by the way, this value 9.8, oh, hold on. This value of 9.81 meters per second squared is called lowercase g. Okay, so anytime you see a lowercase g, that's what it means, 9.81 meters per second squared. It doesn't have the negative into it, so because the negative is just a direction and it depends on your coordinate system. So you have to add the negative where if there needs to be a negative. Okay. Anybody have any questions about any of this? So this is the meanings of those three big vector variables that we're going to deal with. And we're going to use these in the constant acceleration equations for 2D. So the next thing we're going to do is just introduce the 2D versions of these constant acceleration equations. Okay. So the meanings of all this stuff are so similar to the meanings in 1D. You really don't need new storage space in your brain for this stuff. Just notice the similarities, you know. We're basically just following all the same stuff we did before, but for vectors. So this time, P sub I and V sub I are the position and velocity at the time t equals 0. And P sub F and V sub F are the position and velocity at time t sub F. And to use these equations, we're going to have to deal with the subscripts that tell us whether we have x components or y components. So an x subscript of a vector means the x component. And a y subscript means a y component. And with all that stuff, there are 6 constant acceleration equations. But I want you to notice they have the exact same form as the 3 constant acceleration equations in 1D. So here's what they are. I'm going to start out by writing the three that we had for 1D. So V final is equal to V initial. And I'm spreading them out here because I'm going to put some extra subscripts in here, so leave space here. But V initial plus A times time final. And then leave space for one more equation. And the second one from 1D was P sub F is equal to P sub I plus V sub I TF. We'll leave a little more room. Plus 1/2 A times TF squared. And then the last one says 2a times the quantity PF minus PI is equal to VF squared minus VI squared. Okay?
So these can also be used in 2D?
Yeah. And so the way that we're going to use them in 2D is every one of these, I'm going to just copy these out of laziness and whatnot, but if you're taking notes on an electronic computer like me, you can also do that. What the hell? It wants me to copy them by hand. Oh yeah, there we go. Okay, so now I have, and now I'm going to copy this one. Now I'm going to copy this one. Okay. And so here's how it works. One of these is going to be for all the X components. And one of them is going to be for all the Y components. So everything that's a vector is going to have an equation with X components and an equation with Y components. Time final. Time isn't a vector. Time is still just a number. It means the same thing it did in 1D. So we're not going to mess with time in any of these equations. But everything else, do you see what I did? Follow what I did there? Okay, so I introduced the idea of position vector, velocity vector, and acceleration vector. So position, velocity, and acceleration all have an X and a Y component. And so in each one of these equations, we're going to choose either X components or Y components on position, velocity, and acceleration. So here's the X equation for that velocity equation, and then this one is the Y equation. It only has Y components. And I'm going to do the same thing for this second equation. First, there's going to be one with only X components. So PFX is equal to PIX plus VIX times time final plus 1/2 AX times time final. And then the next one is going to be all Y components. So PFY is equal to PIY plus VIY times TF plus 1/2 AYTF squared. I said that funny, and now I have no idea how far behind everyone is on writing this. You need another minute to write all this stuff down. Yeah. Okay. And then with the last two, same thing. So 2a X component times the quantity PFX minus PIX is equal to VFX squared minus VIX squared. That's the X equation. And then the Y equation says 2AY times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. And so remember, in 1D, we had these 3 equations, and there were a total of 6 variables that appeared in all those equations, and we could just cross them off as we figured out which ones we knew and stuff. Now there's 11 if you consider all the components. So there's 11 total variables. And those are time final, X and Y components of acceleration, X and Y components of initial position, X and Y components of final position, X and Y components of the initial velocity, and X and Y components of the final velocity. So that comes out to 11 total. And now, just like I did in 1D, I'm going to give a set of general steps for how to do these 2D problems. And then we'll just spend a couple days doing example problems. So here are the general steps. For 2D constant acceleration problems. The first one, well, what's the first step that I mention in doing 1D constant acceleration problems? Yeah.
Place the stickers.
Yeah, the stickers and the stopwatch. And we're going to do the same thing here. So in the real world, choose where your coordinate system origin is going to be. The orientation of your coordinate system. Your time equals 0 instant. And your time final instant. What's the second step in 1D constant acceleration equation stuff? Yep.
Where's the 0 starting? The starting point?
The next thing we do, so that's kind of defined by this. So that's sort of all one step. And the next thing is just listing out, go through the list of variables and figure out which ones we know and which one we're trying to calculate. Okay. So list the variables we know and want. And again, you can just go through the list. It's just the list is longer now, you know. Once you have those listed out, what's the next step?
See which one of these you can plug in.
Yes, exactly. So now all we're trying to do is find an equation that has the desired variable and every other variable is known. Is there always an equation that works like that?
No,
No, sometimes you get unlucky. And so just like before,
you got to figure out A or D.
yep. So this time in 2D, I think pretty much the only problems we're going to do are free fall problems, which means we pretty much always know A. And so if no equation works, solve for time final. And go back and, go back to step 2. And I want to point out something, a magical power that time final has in 2 dimensions. Look at these equations. So let's just look at the first 2 equations. There's an x equation and a y equation for this v final pair, right? And there are no y components in the x equation, and there are no x components in the y equation. But there's one variable that crosses over between the 2, and that's time, okay? So there are going to be a lot of cases where the most common pair is going to be the p final equation. There's going to be a lot of cases where, say, we'll use the y equation to calculate time final, and then we'll plug that value of time final we found into the x version of the same equation. Okay, that's going to be a really common thing in 2D. That's sort of the unique strength of finding that time final. You can cross between the 2 different components. Okay. Okay, I'm going to do one example problem, and then we'll do the quiz. So let's say a ball is thrown horizontally with a speed of 10 meters per second from a height of 4 meters. How far does the ball travel horizontally before it hits the ground? Okay, so let me draw what's going on here. So here's the ground. And this is 4 meters. And the ball is launched or thrown horizontally at 10 meters per second. And it's going to follow a parabolic path down to the ground. And we want to know what this distance is. Okay? So the first step is we need to choose a coordinate system, how we want our coordinate system aligned, and where we want to put the origin. And I'm always going to do pretty much the same thing. I'm going to always put my coordinate system on the ground beneath where the object is at the start of the motion. Okay, so I'm going to put my origin here. You don't have to do that. You can put it wherever you want, but that's what I'm going to keep doing. And I'm going to choose my y-axis up and my x-axis in the direction of the motion horizontally. And then just like in 1D, we're going to choose when to turn the stopwatch on and off based on where we have information or where we're trying to find information. So what's going to be the instant where we click the stopwatch on? Yep. So it's going to be the instant that it's, released or thrown. And what's going to be our time final? Yeah, I'm going to write it as when it reaches the height of the ground. And the nice thing about always putting the origin of the coordinate system on the ground is when it reaches the height of the ground, that's saying that the y position is 0. Okay. All right, so we made those choices, and now we're going to figure out what variables we know and what variables we want. Do we know how long it takes? No. Do we know the acceleration? It's free fall, yeah. So we know that it's down at 9.81. So I'm going to write this vector as, since my y component, my y-axis is up, we know that the acceleration is 0 for x and negative 9.81 for y. Do we know the position at time equals 0? So in other words, do we know the coordinates of the ball at time equals 0? Yep. What are the coordinates? Yep. Perfect. Do we know anything about the coordinates of the ball when it reaches the ground level?
We know the y.
Perfect. Yep. So we know that P F y is equal to 0. P F x is what we're trying to find. Do we know anything about the velocity at time equals 0?
Yes.
Yes. We know the speed, and from the direction we can figure out the components. So if our coordinate system is aligned like this, and our velocity is horizontal with a magnitude of 10, what are the components of that vector?
Y is 0.
That's right, y is 0.
No, that should be 10 meters
Yep.
per second.
That's right. So VI is 10, 0. And then do we know anything about the velocity when at time final? 0. That is an easy thing to think, but it's not true, because remember that we are just calculating the velocity. Like, we're doing this calculation assuming that there's kind of no ground there, or you can also think of it as like we're calculating what's happening the instant before it hits the ground. Once it hits the ground, it doesn't have constant acceleration anymore. It's not in projectile motion, so we can't use that. So no, we don't know anything about the velocity at time final. So we just have to leave that out. Okay, so is there any equation that'll let us calculate PFX? It turns out if you go through all those equations, no, there's nothing that works. A way to make this a little quicker is remember that any x components are not going to show up in the y equation. So that immediately cuts us down to only 3 equations to consider to look for this. Okay? And then those 3 don't work. So no equation works, and so we want to calculate time final. And the equation that works to find time final is this one. P F Y is equal to P I Y plus V I Y T F plus 1/2 A Y T F squared. And just plug in our values. So we have 0 is equal to 4 plus VIY is 0, so this whole term goes away, minus 4.905 TF squared. Do the algebra and you get that TF is equal to plus or minus 0.90 seconds. Yes?
Did you get a negative 4.9 from the half and 9.8?
Yeah, that's right. Yep. Okay, which one do we want, the positive or negative time? Yeah, we only have positive times in this whole class, so that's an easy choice. And now that we know time final, that's one more thing in our column of stuff we know. And now we see that we can use this equation to calculate PFX. So PFX is equal to, PIX was 0, VIX is 10, what's AX? This is something you have to be careful of because we're used to just always using negative 9.81 for A, but the X component of the acceleration is 0, so this term goes away. And we get that PFX is equal to 9.0 meters. So this ball hit the ground 9 meters away horizontally. Any questions about that? Okay, I'll give you a couple of problems to try to work through for Tuesday. And feel free to, like, if you have questions you can't figure out what to do, I'd be happy to work through any of them on Tuesday. Yeah.
For our first exam on Thursday.
Yeah.
Will it be up to here?
Okay, good question. Yeah. So exam 1 is next Thursday, and it won't have any of this stuff on it. It'll just be up through vectors.
So also all vectors.
It will include vectors, but none of the stuff we did today. Well, none of the position velocity stuff that we did today.
Thank you.